Okay, the first set of changes we're going to look at are changes to the right-hand side. What happens if we change our B vector? I'm going to use the sort of notation of putting a bar above any variable or any vector that's being changed, uh, just to kind of denote what's changing. Okay, and so we'll change B to B bar, and we'll essentially look at changes to each of the individual parts of that. Okay, looking back at what changes in our final tableau, the only place where the B vector shows up is in the right-hand side in the objective value and in the basic solution. And so those are the only things that are going to change. Changing those will change the amount of the optimal solution, and it might change the feasibility. Okay. If it remains feasible, though, it will remain optimal because that B vector doesn't show up at all in the optimality conditions. So the only thing we need to check as far as is whether we're still feasible. Okay, so small changes in B will kind of change the objective value to Y transpose times B bar, and then also change our basic solution to B inverse times B bar. Let's look at the range for which that remains valid. So it's valid for small changes, but essentially how far can we change each of the B1, B2, and B3 and still have that remain valid? So it's, I'll maybe copy that down, feasible if B inverse B bar, which I guess is what we'll call XB bar, is greater than or equal to 0. So let's go ahead and pull out what is B inverse. Well, looking back at our problem here, we can read off B inverse as being essentially the matrix that's underneath our slack variables. And so here's that B inverse. And I'll go ahead and copy it down onto this page. And so we've got 1, -1, 0, -1, 2, 0, and -1, 1, 1. So that is our B inverse matrix. And then we're going to make changes to B. And so we'll call this B1 bar, B2 bar, and B3 bar. Let's do that multiplication. And so multiplying this down, we'll get B1 minus B2. This one will get negative B1 plus 2B2. And then the last row will be negative B1 plus B2 plus B3. Okay, and this is essentially our X bar B. So our new basic solution after making a tweak to the right-hand side. And we want that to be greater than or equal to 0 for us to remain feasible. So in essence, each of these, we get 3 inequalities that this, and this need to be greater than or equal to 0. So we could kind of look at all those changes simultaneously. It would essentially be saying that we have these 3 inequalities, that each of these 3 things need to be greater than or equal to 0. That's fine. If you had a specific set of changes, you could evaluate kind of all those changes simultaneously. But usually the kind of approach is to evaluate the changes one by one. And so let's look at changes to B1 while keeping all the others the same. And so maybe it'll be helpful maybe to write down the original values of the B vector. The original values of the B vector were 100, 80, and 40. Okay, so now let's look at each of the changes to each of the parts separately. So B1 changes. And we want to find a range where we can change B1 and still have the current basis remain feasible. If we move it more than that, then we're going to have to essentially change our basis. Okay, so let's look at this first one. The first constraint here is that we'll have B1 bar minus, and then we're going to keep B2 the same, and B2 was originally 80, so we'll get B1 bar minus 80 has to be greater than or equal to 0. Second constraint becomes negative B1 bar plus 2B2, so plus 160. We're keeping B2 locked at its original value. And then here, this constraint becomes negative B1 bar plus B2 plus B3. And so 80 plus 40, so plus 120, greater than or equal to 0. And now we want to essentially come up with what's the region where all three of these constraints are true. Okay, rewriting this one, we get that this one says that B1 bar is greater than or equal to 80, adding this 80 over to the other side. In this case, we got a negative here, so I'm actually going to add the B1 over to the other side. And so this one tells me that 160 is bigger than or equal to B1 bar. This one, I'll move the B1 bar over to the other side, and that would tell me 120 is greater than or equal to B1 bar. Okay, I need all three of these to be true in order to still have a feasible solution. And so looking at the range where all three of these are going to be true is that I'll have 120 has to be bigger than or equal to B1 bar has to be bigger than or equal to 80. So as long as B1 bar is between 80 and 120, all of these will be conditions will be true, because if B1 is less than 120, then it's also going to be less than 160. Okay, and so as long as B1 stays in this range, then our current basis stays optimal. Okay, so the idea is that you'll get, in this sense, three inequalities. You can kind of think about them as constraints on B's. Three inequalities related to your B's. You're going to only change one of the B elements at a time, lock in the other values at their original values, so whatever they are in here. So this is sort of the original B1, B2, and B3. And then you'll get several constraints, solve for essentially the region that satisfies all those constraints. Okay, let's do B2. So now we're going to let B2 be our unknown that we can slide around. Yeah, but B1 and B3 are going to be locked in at their original values. So the first one will look like 100 minus B2 is greater than or equal to 0. Second one, it will be negative 100 plus 2B2 is greater than or equal to 0. And then the last one will be negative 100 plus B2 plus 40 is greater than or equal to 0. Okay, let's go ahead and move these around. This one says that 100 is greater than or equal to B2, moving the B2 over the other side. This one, I'd add the 100 to the other side and then divide by 2. Thing to remember with inequalities, if you divide by a positive number, that's just fine. If you divide by a negative number, you got to swap the inequality, swap the direction of the inequality. Okay. So here I'm going to add 100 to both sides, divide by 2, and that will give us B2 is bigger than or equal to 50. And then this one, let's see, that will give us negative 60 added over to the other side. And this one will say that B2 is greater than or equal to 60. Okay, where are all these changes true? Well, I've sort of got 2 lower bounds and 1 upper bound. And so 100 is going to be my upper bound for B2, and then I'll have to take the larger of the 2 lower bounds, and so I'll say 60. So between 60 and 100 for B2, maybe I keep forgetting my bars because these are the ones that are changing. Bar kind of indicates change. So anywhere between 60 and 100, Notice that if B2 is bigger than 60, we know it's also going to be bigger than 50. And so, yeah, one of the inequalities ends up sort of being redundant if you got three of them. Sometimes two of them become redundant or more than that. But yeah, some of those inequalities will become redundant. Okay, go ahead and try out, pause the video and see if you can figure out what are the inequalities for B3. Okay, you should have gotten these three inequalities. Notice the first two inequalities don't involve B3 at all. They only involve B1 and B2. And so this one says 20 is greater than or equal to 0, and this one says that 60 is greater than or equal to 0. Both of these are true statements, but they don't tell you anything about B3. So the only piece of information we get is this last inequality here that says that B3 bar should be greater than or equal to 20. Okay, and so for B3, we only have a lower bound, which is actually not surprising, because if we think about our third constraint, it's the one where we have some slack. And so as long as we don't reduce the amount of demand for soldiers below 20, then we've got plenty of demand for soldiers, and increasing the demand for soldiers won't change anything. And so maybe I'll summarize this here is that B3 bar is greater than or equal to 20. Okay, so as long as we are only changing one of the three, this will give us our limits on how far we can change them before our current basis becomes infeasible. Okay, let's look at these ones visually, and I'll kind of show you what happens. So the range here for B1 is between 80 to 120. Let's go back to that Desmos graph. Okay, and so here's B1, and we'll slide it down until it goes down to 80 here. And at 80, what was our optimal solution has now slid up to here. And if we go lower than 80, that corner point that was our basis, remember our basis is essentially choosing which intersecting constraints we're at. And our basis is essentially at the intersection of these two constraints. And so it's going to be this point here. But if I go below 80 for the value of B1, that corner point or that basis becomes infeasible. Okay, we get a negative value there. On the other hand, if I right at 80, sort of two corner points line up with each other. If we go the other direction, and here I'm going up to 120, we'll notice that corner points line up with each other. And if I go past 120, then the corner point here goes outside of the feasible region. This is the feasible region over here. We're on the wrong side of this demand for soldiers constraint. Okay, and so between 80 and 120, our optimal solution will move wherever this dot moves. And so, oopsie. So in between there, those changes will change the amount of profit that we have, our objective value. They'll also change what our optimal solution is. So here at 105, our optimal solution is now 25-55, 25 soldiers, 55 trains. And so change those, but it will still be the same basis. Okay. If we change more than 80 to 120, then we're no longer feasible. Okay. So that's kind of investigating changes to the right-hand side. And maybe the last thing to kind of recall is also that aspect of shadow prices. I can use the shadow prices to tell how much the objective will change for each unit change in the B variables. And so because my shadow prices were 1, 1, and 0, then any one unit change to B1 corresponds to a 1 unit change in Z, because there's a shadow price of 1. If there were a shadow price of 2, then it would increase Z by 2. Correspondingly, if I reduce those resources, let's say there's cutbacks in labor or somebody quits, right? As long as it's a small amount of labor lost, maybe someone actually gets sick for a day, then let's see, yeah, then we'd have a reduction in B1 or B2, and those would lead to a reduction in the profit. Okay, and so yeah, those shadow prices tell you how much the objective changes as well for those changes in the B vector. That's it for this video. The next video will look at adding a new variable. What happens if we consider a new product?